Hello, welcome to the August 8th, The Nutritionist webinar. I'm Marianne Fessenden from AMTS and your English language host. This monthly webinar series is dedicated to providing technical talks from internationally recognized educators for listeners around the world. Elena Bonfante from Dairy Innovations Italia co-hosts in Italian. Paula Turillo from Cordoba, Argentina translates and hosts the Spanish language webinar. Tom Long from Hemingway in China will be hosting in Mandarin. There will be a question and answer period immediately following the presentation. Listeners can submit queries through me, Paula, or Tom. Later, a complete recording of archived webinars, as well as the question and answer session for each, will be available on the AMTS website. For those of you who would listen to the presentation whilst driving, we have converted the videos into MP3 files that can be downloaded for your device for offline listening. This month, we are pleased to host Dr. Heidi Rossow, an Associate Professor of Ruminant Nutrition with UC Davis Veterinary School. After receiving her PhD from UC Davis, she used her extension experience in mathematical models designed to understand nutrient flow in and out of the cow to develop a standalone program that evaluates rations and cow performance. She works at the Veterinary Medicine Teaching and Research Center in Tulare, California, where her areas of research include computer modeling of nutrient metabolism, systems analysis of dairy feed management and production, and developing nutrition monitoring programs. In this presentation, Dr. Rossow joined me on Monday afternoon to record her talk to enable broadcasts twice today at 9 a.m. and 6 p.m. She will be with us for the live question period. For our audience, if you have questions during the presentation, please type them in the chat or Q&A window. Heidi will answer them at the end of her presentation. We will now listen to her talk.
Today I am talking about managing excretion. And so there's really two different levels that I want to talk to you about this. There's how managing excretion, how it can be done at the cow level. And then I want to talk a little bit also about what other concerns there are at the dairy, the whole dairy level. Usually when we talk about regulations around being able to manage excretion, we're usually talking about minimizing nutrient deposition in the environment. And so there's differences in how we consider that both at the individual cow level and then it's different also at the dairy level. So I am located, just to give you an idea of where I am, I'm located in California, really right in the middle of the dairy industry in California. So the Tulare County, Kings County area where most of the cows are. And the reason why I want to go over this is because these are relatively large dairy herds with large pens of cows. And most of the data, probably more than half of the data I'm going to be talking about, is actually from this area of California. And I need to recognize my cohorts in the Ag and Natural Resources part of the university, the Extension Service, who has done a lot of this work. People like Peter Robinson, Frank Mitloner, Dan Meyer, the other farm advisors in California, those are extension specialists, and then also Marsha Campbell Matthews, who have really done quite a bit of data collection and looking at how managing excretion is both ways to do it at the cow level and then again also at the whole dairy level. Okay, so just to give you an idea of the size of the herds in California, this is just a general view of our average herd size in Tulare. We even run a little bit larger than all of California, with about 1,750 cows per dairy. So our herds are actually fairly large, and most of our dairies are actually considered concentrating feeding operations. So we actually don't have a lot of pasture associated with our dairies. We do have herds every once in a while that will take their young stock, the heifers that aren't pregnant, between weaning and getting them pregnant, and they will actually move them up to mountain or hillside pastures and leave them there for a few months to kind of gain size and weight, and it kind of takes some of the stress of feeding off the dairy operation to move them up into the pastures. But by and large, we do not really have any pasture associated with these dairies. And so what I'm going to talk to you about today, as far as managing excretions goes, is really 4 areas. And in all these areas, I want to talk the difference between how we would manage excretions between the cow, looking at the individual cow, and then also looking at managing excretions for the whole dairy. So I'm going to talk about that first, and then I want to talk about the concept of nutrient balance and what it means at both the cow and dairy levels. And then also talk about efficiency, what numbers are used for efficiency, and what efficiency really means. And then finally, in the third section, what I want to talk about is strategies. So what strategies can we use for managing excretions both at the cow level and then also, again, at the dairy level. So at the cow level, when we're usually talking about managing excretion, we're talking about manipulating the physiology and the metabolism of the cow. So this is going to concern things like what's the requirements of the cow. When we formulate a diet for a cow that is actually going to be fed to a pen of cows, are you formulating that diet for the requirements of the average cow in the pen, or are you adding safety factors in to make sure that you can meet the requirements of the cows that are the higher producers and the upper level of the distribution of cows that happen to be within that pen? Then also diet. Of course, the more digestible a diet is, the less chance nutrients coming in are actually going to be excreted. So digestibility is a very important component of this. The concentration of nutrients in the diet, what the production level of the cows are, because producing milk is one way to pull nutrients out, and the more milk they produce, in theory, the less nutrients that are going to be excreted. Also, what environment, what the temperatures are for the cow, are they dealing with any stresses, what the health the cows are, the ability of the cows to retain, and the retention is actually related to endogenous sources for some of these nutrients. So I'll be mostly talking about nitrogen, phosphorus, and potassium, but how we are able to maybe measure some of those endogenous sources, what time frame we're measuring those things over. Is it following one cow through entire lactation, or is it looking at a snapshot of the dairy where we're looking at cows at multiple different stages of lactation and trying to figure out what their excretion is for the entire dairy? And then, of course, genetics always plays a role in what the production level of the cow is, the ability to digest, and then, of course, the ultimate response would be what nutrients are actually excreted. So one of the things that I want to bring up in this, especially with a lot of the work that we do on commercial cow herds, is that a cow's ability to turn nutrients into product really does vary. So when we're talking about an average cow for a pen, we have to understand that especially in these large pens, there's a huge distribution of response in milk production for what those cows actually do produce. And so this is a graph that shows data from actually a relatively old study, and this is weekly milk totals from cows that were milked 3 times a day. And you can see the red line kind of in the background is actually the average milk production for the pen. But the blue dots represent individual cow milk production, and you can see how much it varies across a group of cows or across the pen. And so the fact that the milk production varies lets us know that dry matter intake also varies a lot. And so how do we actually manage this variation so that we actually, again, capture the nutrient excretions, not only are able to predict it, but are able to actually manage it across a wide range of nutrients that can actually possibly be excreted by the cows due to the variability. So that's talking about the individual cow. So I want to define what I'm talking about relative to the farm management and managing excretion relative to the farm, and why this is so different from managing individual cows. For one thing, the farm excretion really is dependent on how the dairy is managed. So how is the manure managed? How is it collected? How is it processed? Is it recycled and used for bedding? Is it dried and used for fertilizer? Is it dried and used for compost? Is it dried and used, go to a lagoon and that lagoon runoff is used for as a fertilizer to crops? What types of facilities do they have that helps them manage the manure? how much are the nutrient imports, in other words, purchased feeds that might be coming in, birthing and culling rates on cows, because that's considered a nutrient export. Weather is really important because how much rain is actually being dumped on the dairy property, where does the runoff go to? Does it enter the waste stream? And feeding the entire dairy shrink's very important, because where does that feed go that you can't account for between the feed that you purchased and the feed that actually gets delivered to the cow? Is it potentially also going to end up in the waste stream or the manure chain of management or processing? Nutrient recycling, like I mentioned about, are we collecting that manure and using it as a flush, or is it going to be used as a flush and or also then as fertilizer later on? What crops are grown? What's the ability of these crops to actually remove nutrients from the dairy property and either be sold or again be recycled and fed back to the cows? And then of course feed management has a big role in this also, as we deliver feed to the cows, but what actually ends up with the feed that's actually refused by the cows? Does that get refed somewhere else? What happens to the mold layer on the silage piles? Does it enter the waste stream or does it get fed? And then again, what type of facilities? We talked about that. And even down to what's the grouping of the cows? How are cows grouped? How big the pens are, things like this. So these things are all really important concepts when you're talking about how the farm actually manages manure relative to how you're actually going to deal with the cow with her individual excretion. And this diagram really kind of captures that. Down looking at the inputs, you've got purchased feed, purchased fertilizer. If you're purchasing a legume such as alfalfa hay, what nitrogen is it supplying into the waste stream? And also, of course, rainfall, like I mentioned before. And then we have the outputs that can get exported off farm, which would be animal products. And of course, in the case of dairy, the big one is milk. And then also any crops that are sold. And then incorporated in this is the concept of losses that we can't account for. So things like ammonia volatilization, leaching of nitrogen down into the soil and into the water, runoff, erosion, all those kinds of things. All of those affect how we manage excretion on the farm. And so just like we're talking about variability relative to the individual cow, farm management also incorporates its own sense of variability within managing the farm also. So what I have here, this is results from a study that we ran probably about 5 years ago in the Tulare area. And what we were looking at is we just wanted to know what the variability is on feeding a TMR over 8 weeks. And so what we did is we collected a sample once a week, and then we looked at what the coefficient of variation was on the nutrients that were supplied to these cows over the 8-week period of time. And so that top graph shows you the close-up cow group. The second graph shows you the fresh cows from 0 to 21 days in milk. And then the third graph shows you the coefficients of variation of different feed ingredients in the high group. So that's 21 to 150 days in milk. We did this for 5 dairies, and you can see the color coding in the upper right-hand corner for those 5 different dairies. And you can see the nutrients, the columns of nutrients down at the bottom. So we looked at everything from dry matter to crude protein, all the way over to some common minerals that we would assess in the feeds. And what you can get from this is that, yes, there is quite a bit of variation in feed delivered, depending on the dairy, depending on the pen, depending on the diet. And this variation, of course, contributes to variability on cow response. It contributes also to what the variability we see in the feed management, and of course also the variability of what possibly might end up in the waste stream too, because that variability is also going to translate into manure produced by the pen. So this is an example that management really can introduce a lot of variability. And one of the most important things when you're dealing with anything to do with milk production on a dairy is being able to understand that variability both at the cow level and the whole farm level to really get a good handle on what you're dealing with the entire dairy, and not just looking with an average of what happens on the dairy. Because variability is one of the things that the more you can reduce it, it seems like the happier the cows are, the more efficient the dairy is, and actually the more profitable the dairy is too. So to just kind of summarize my initial section on talking about managing excretion at the cow versus at the whole dairy level, what we're going to be talking about, of course, later is feeding strategies to minimize excretion. Most of those feeding strategies are actually at the cow level, so you have an understanding that, yes, if you do reduce manure nutrient excretion, yes, probably for the whole dairy you will see a decrease in the manure nutrients that are actually end up in the manure waste stream for the entire dairy. The second point I want to get across is that the importance of managing excretion at the cow level really depends on farm management, and that's what we saw with both of those variability graphs. Of course, milk production is very dependent on feeding, and if you have a lot of variability in feeding, you're going to also have a lot of variability in milk production. And so when you have variability with that, with milk production, again, you're going to also have variability in the excretion of nutrients too. And again, that's going to be very dependent on farm management like we discussed. Variability at both the cow and dairy level needs to be considered, especially in large herds, because we really do see more variability in large herds in large pens, and that's one of the issues with large dairies is how do we manage the entire pen to actually minimize that variability as much as possible, because again, that leads to a happy, healthier cows and also leads to a more profitable dairy. So the next section I want to talk about when we're talking about managing excretions is actually the concept of nutrient balance. And nutrient balance is the primary idea behind, at least in California, the regulations that have been handed down to us for dealing with dairy nutrient waste. And so I'll be explaining that a little bit more later on. What I want to talk about first, though, is, again, at the cow level, what nutrient balance means. And by definition, it's pretty much what goes in, so feed, water, what goes in, what comes out as far as production levels, so maybe weight gain, milk production definitely, because that's a large contribution, and then of course what comes out of the cow, which would be the manure, and possibly cows, carcasses from cows dying, any bull calves that are produced, things like that. Those could all be considered output at the cow level. And so this diagram is really just shows you a basic nutrient flow for a cow, an individual cow, with nitrogen, phosphorus, and potassium. On the intake, it assumes a 66% digestion of those nutrients, and of course, if you look at this, you can tell right away that if we can increase digestion, we can reduce the amount of nutrients probably coming out in manure. Notice a couple things. Number one, quite a bit of nitrogen comes out that was fed, comes out in manure, and the same is also true for phosphorus. But potassium appears to be a little bit more efficient. And you can also notice, too, on the milk production that the rest of it basically is attributed to nitrogen, phosphorus, and potassium that ends up in milk. So milk is a major contributor to where nutrients go, and that's, of course, considered a useful product because it's profitable. But I want to bring home the point that actually manure is a pretty big sink for a lot of those nutrients. If we look at nutrient balance on the whole farm level, the default assumption in regulation really is that what they want is they want to see nutrient import be less than or equal to export. And that's what most of our regulations and farm balances that are part of the nutrient management plans that our farmers have to submit, that's what they really want to see, what the regulators want to see. So they don't want to see a net buildup of any one nutrient on the farm, and that's why they're looking for import to be less than or equal to export. And so this is, again, a diagram that pretty much just shows you some of the inputs and outputs that would be considered on a whole farm. So you can consider inputs to be rain, purchased feed, fertilizer. And if you look at those three, you look on that diagram, purchased feed and fertilizer, in this particular example, it's potassium. Notice that they are relatively really large inputs into this cycle. Outputs that you can commonly see are groundwater leaching, milk, also calves, and of course compost from the manure. And of course, on the outputs, like I said before, one of the biggest outputs is milk. So if you can increase milk production of the dairy without increasing nutrients that go into the dairy, you actually get an increase in efficiency, and you also get a better nutrient balance across the entire dairy. So one of the things we tried to do with the group of extension specialists, and I was helping on the modeling side, is we really wanted to look at nutrient balance on a whole farm and build a model of it to look at in the waste stream where these nutrients are going to and what kinds of technologies might actually be able to help us manage the waste stream, control where the nutrients go, and maybe lead us to some good conclusions on how we can actually manage the waste stream. And so to understand that, we put together this diagram that is not really specific to one dairy. What it actually does is it shows all the possible directions that nutrients can go in the waste stream of a dairy. And so what you see, and of course we were trying to do it for nitrogen, phosphorus, and potassium, so we're really looking at trying to calculate what the mass balance is for the nitrogen, phosphorus, and potassium. So we have the import sources, which would be manure, silage, silage leaching, feed dust, and bedding also. And of course that all ends up in the waste stream, which is that manure collection box you see at the very top. So that would be the total nutrients we're starting with. And then you have options on how you pick those up. You have scraping, you can have vacuuming, which not many of our dairies do anymore because of the cost of fuel. And you can also have flushing. And from what comes out of those three possibles, from there it can go to a solid separator, or it can come out as solids, and those solids can be composted. If it goes through a separator, it can go to a lagoon or to a pond, and that runoff or effluent then can be applied to land. And if it's going the compost route, it can go to compost, and that compost can be applied to land, or it can be taken back and used as bedding actually on the dairy. So that just gives you an overview of kind of what we were thinking as far as what are the possible routes for this to go. So what came out of this was we actually then went out and collected data from a dairy, a real dairy in California. And what we wanted to do is actually get estimates from measurements of how much nutrients were in each section of the waste stream. So this is the nutrient balance for the dairy, and you can see there's different classifications that kind of help guide you through the dairy. So this is a real map of the dairy and where manure flows through that dairy. So in the first part, you've got the feed operations, which would be silage, hay, commodities, and sorry, I know the writing's kind of small, but it's a really big diagram. And then down below that, you also have fresh water, so washing if through the cows, and if you're not washing the cows, then through the milking machines, cows drinking, and of course any water that's used in cow cooling. So those are the basic feed operation inputs. And then we have the housing, milking uses for water and where the nutrients end up there. And we have parlor water, free stalls, manure collections, recycled flush water down below. So I want to explain this diagram a little bit, because what we did is we actually collected samples of the water in each parts of these and measured what the nitrogen and phosphorus contents of that water actually was all along. So when you see the O, that's actually what we call the observed, and so that's the numbers that we got by doing actual measurements on the dairy. The P stands for predicted, which is, again, there was a model, a computer model that went along with this. And so the predicted is what the model was predicting. So I'm not going to be talking about the P's very much. But what I do want you to notice is there are also some S's, like particularly if you look at the screen in box, you can see it's observed, predicted, and then it also has an S number. The S is the standard deviation on those estimates. And so by doing this diagram and trying to lay out and follow where these manure nutrients were going through the entire dairy, there's a couple conclusions that we came to through running this model. And so I want to go over just some of the major ones with this. In looking at this, one thing that we found was that the contribution of daily manure to the flush, and of course this is a freestall dairy, was relatively small relative to the entire flush. So what am I talking about? So on this dairy, they had a solid separator, and then the liquid portion, which actually happens to hold most of the nutrients. If you look on this, most of the nitrogen and stuff doesn't go to the solids collection after the screen. It actually goes to the liquid portion on the screen. That would go out to a lagoon, and that lagoon water then was used in the flush to flush the free stalls. So what we found with the model was that after running the model for about 30 days, the daily contributions of manure in that flush to the waste stream was actually relatively small, and it was kind of asymptotic. So the total amount of nutrients in that flush were actually stayed fairly constant after about 30 days. So that was the first thing that was really interesting to us, is that you actually kind of plateaued on the amount of nutrients that were in the recycled flush water. The second thing, and I kind of mentioned this already before, was that actually most of the nutrients in the waste stream were captured when it went through the screen separator. It was actually captured in the liquid portion, and there weren't really very many nutrients in the solids portion. So this is important because what ends up happening in the lagoons is you end up with most of the nitrogen and phosphorus going out to the lagoon, and of course there's a lot of anaerobic fermentation by bacteria in that lagoon, and that ends up stratifying. So you end up with a sludge layer down at the bottom that if you don't have mixing in the lagoon kind of stays there. And then just like you have stratification in the rumen of a cow, you also would have stratification in the lagoon. So what nutrients you found and the relative amounts of microbial degradation of those nutrients in the lagoon was different for how far down you go. This is important because if you want to sample lagoon water because you're going to use it for manure application, depending on what layer or how far down you go in the lagoon, you're going to get very drastically different results in what nutrients are actually present in the lagoon. So this is an important thing to understand also. And probably the third thing that's really, really important is that when you look at the S numbers here for a lot of these boxes, what you find is the standard deviations of these O values, the observed values, or what we measured. The standard deviations are actually very, very high. And in some cases, they are as high as the number that we're trying to actually predict. So what does this mean? This means that it's really difficult to go out on a dairy and actually get a good estimate of what the nutrient flow is through that dairy. This means that mass balances of dairies, if you're doing from this approach, it's very error prone. And it also means that if you're trying to use a model like this to identify critical control points for where you want to either measure or manage the manure, you can't do it using this method because the standard deviations are so high, you can't really trust the averages that you get. And this is part of my continuing kind of flow through this talk, is that variability is really important. And you can't just take an average value for a lot of these things because especially at the whole farm level, there is a lot of variability on any one of these measurements that you make. So you really need to estimate the variability to know how good your averages are. Okay, so if we look at another comparison looking at cow, this time looking at cow manure excretion versus the dairy balance excretion. So I have cow in the left-hand column and I have farm in the right-hand column. And remember with cow, when we're talking about balance, we're talking about inputs and then the outputs. I'm only considering manure and milk in the outputs here. And then on the farm, when we're talking about balance, we're talking about imports being less than or equal to exports, or in another way of putting it, in minus out has to be less than or equal to 0. And so these numbers on the cow side, of course, are in kilograms. The numbers on the farm side are in, this is only on the whole farm side, we're only considering nitrogen in tons per year. And so on the cow side, if you assume a 17% crude protein diet, it shows the nitrogen balance, an estimated nitrogen balance, and this is from published literature, and the references are down at the bottom of the slide, that the input estimated for nitrogen was 0.64 kilograms, the manure output was estimated to be 0.36 kilograms, and the milk output was estimated to be 0.16 kilograms of nitrogen. And so that actually has a positive balance, that it's a net input into the system of 0.12 kilograms. And so all these further on down read pretty much the same way in the cow column. You've got phosphorus balance, that's a positive balance. It's actually very, very small. It's almost 0, so that would be good. And the potassium balance, you can look at that for the cow for this particular estimate. It's also relatively small and pretty close to 0. If you look at the farm side, you can see that we can look at the inputs, which are at the top, and that's purchased feed, purchased fertilizer, bedding. And I have a question mark by bedding because, of course, some of our dairies do use manure as bedding, composted manure as bedding, and some of them actually bring in sand. And that's pretty much, some will use almond hulls, but on a almond shells, but on a very limited basis. It's mostly sand and sand or manure. So that could be an input or maybe a recycled nutrient input if they use manure solids as bedding. And of course, then legume fixation, that can also be considered an input because that's a contribution, if you're growing alfalfa, contribution of nitrogen to the soil of the farm. And that, if you sum all those up, the inputs are 118.5 tons of nitrogen per year. What I really want to point out on the inputs is that of all these inputs, of course, the biggest ones are purchase feed, and also if you buy fertilizer, that's also that's really most of the inputs to this nitrogen balance here for the whole farm. If we look at outputs, you've got milk, 26.4 tons of nitrogen per year. The herds, this would be body weight, this would be culled cows. If there's any crops sold, a lot of times our dairies don't sell any crops really. Any of the crops they grow are forage crops, and they are actually refed to the cows. And then down at the bottom, you sum up the outputs, and you can see, of course, the major contributor to outputs is also milk. And it's actually got a fairly large positive balance across the in versus the out of 90.2 tons of nitrogen per year. And that's about 76% of what the inputs are. So what I really want to show from this is that both the cow and the farm in general are usually in positive balance. And on the farm side, the biggest contributors to inputs is actually feed and fertilizer, and the biggest export is actually milk. So if there's any way that the dairy can actually limit the amount of feed it purchases and the amount of fertilizer it purchases, and then increase its milk production at the same time, it can actually improve its balance to hopefully be closer to zero. One of the things I want to bring up, though, is really the concept of, can zero balance really be possible, and can you even get to the point where your outputs are actually less than what your inputs are? So let's go on with this. And so in summary for the nutrient balance section, nutrient balance for both the cow and the dairy is really a function of what goes in, what stays, and what comes out. And of course, in with that, when you're considering nutrient balance, you really need to consider not just the averages, but have estimations of the variability associated with each one of those, because that's really, they say the devils are in the details, and the variability is really the details. Any way to minimize the variability so that you have good estimates is really a priority in this area, and really all of the area of dairy management. The second point is to really avoid feeding excess. And again, because the largest inputs were feeding and fertilizer, to get to a better nutrient balance, the best thing that can be done is to minimize inputs. And finally, from the modeling that we did on the dairy, right now, I think estimating critical control points in nutrient flow is probably just not possible, because we really have an inability to actually measure, get good estimates of what the nutrient flow is on an actual dairy. It's very hard to measure this due to the variability that we see on dairies. So what I want to do now is talk about the next section. So we've talked about nutrient balance and what the in versus out is for the cow and the dairy. Of course, cows are hardly ever in nutrient balance on an individual basis, but there's cows in lots of different stages of lactation that contribute to what the nutrient balance is of the whole dairy. And part of what actually the numbers that you get for nutrient balance is dependent on how efficient both the cow and the dairy actually are. So the next section I want to talk about is efficiency, and how efficiency contributes to managing excretions, or what nutrients you find in the waste stream. So some of the efficiency guidelines that are being in place and used right now are, number one, the nitrogen use efficiency. So nitrogen with the National Resource Conservation Service in the United States, if nitrogen use efficiency for an entire dairy is less than 30%, they will actually, there's incentives out there to help them get below 30% for the nitrogen use efficiency. And nitrogen use efficiency is defined as the nitrogen in milk for the entire dairy divided by the nitrogen in feed. So you can see nitrogen use efficiency is really defined by what an individual cow is doing. In theory, there shouldn't be much management attached to that, but what really matters is how they're actually measuring the nitrogen in feed. Are they looking at purchased feed? Probably not, because that can be a very difficult thing to track on a dairy, but it is relatively easy to see what nutrients are actually being delivered to the cows. It may not be what they're actually eating, but it's easy to actually tell what the nutrients are that are being delivered to cows. And so that ratio may actually be missing some of the whole farm contributions of nutrients to the waste stream, but because it does consider nitrogen in milk, and of course milk production is a big contributor to net export of nutrients off farm, it is capturing that in the numerator. So the focus, of course, is to either increase milk by get a good nitrogen use efficiency, to increase milk, or to decrease dietary nitrogen. And so what this ratio really tells you is what the milk nitrogen efficiency actually is. Another term that people use a lot for efficiency is called feed conversion efficiency, and the goal is usually to have a feed conversion efficiency of 1.6 or above, and that's just the ratio of kilograms milk to kilograms dry matter intake. So it's similar to the nitrogen use efficiency. You're just looking at it on a total input-out basis, with kilograms milk being the output and kilograms dry matter intake being the input. Okay, so if we talk about efficiency with the cow relative to the farm, and this is just considering it on a nitrogen basis, nitrogen and phosphorus basis for the farm, and this is really the ratio of the output or milk relative to the input or nutrient input in the diet. This is looking at the cow. We can see that it's a 16% crude protein diet that we're estimating this off of, and in the cow it's showing the nitrogen in manure, about 68 to 70% of that nitrogen that goes into the cow actually ends up in the, it's about a 68 to 70% efficiency of nitrogen in manure relative to the 60% crude protein diet that's fed. The milk efficiency is about half of what the nitrogen in manure efficiency is, and if you'll notice, there's also an additional line of urea plus ammonia that's 31 to 34%. That urea plus ammonia is actually considered in that upper line of nitrogen in manure. So in the nitrogen in manure efficiency number, it's actually half of that is really urea and ammonia. And this is important to understand too, is that manure is made up of feces and urine, and the relative sources for each one of those are different, and the impact of what happens to nitrogen in manure in particular is very dependent on what proportion of that is urea and what proportion of that is from organic sources or from feces. If we look at the farm efficiency, the overall farm efficiency for output and over input for nitrogen is actually about 36%. So while the cow is a much higher efficiency, you can see that the farm is only actually about half the efficiency of that getting that nitrogen and manure of what the cow is, and that's just due to the fact that there's a lot of other processes that are happening on the whole farm. And the same is true for phosphorus. You can see that phosphorus capture in the manure is actually very poor, and a lot of phosphorus ends up in milk. And for potassium, a lot of potassium actually ends up in manure, and very little potassium ends up in milk. Whereas the farm actually does is not great as good with nitrogen. It's not as good at phosphorus as it is with nitrogen. I also have some estimates for the cow for calcium, magnesium, and sodium. But the basic point that I want to get across here is that for the farm, the efficiency is actually much lower. This is due to having unproductive stock like heifers that aren't producing any milk. Therefore, that drives the efficiency of the farm down. There's also a greater potential to add to the waste stream when you consider the entire farm, because there's things like loading a mixer wagon. If there's a powdered mineral that's used and it's a windy day, that mineral is going to pretty much go all over the place and may not actually make it into the diet. There can also be environmental losses due to volatilization of nitrogen, and how the urine and the feces mix to actually get the manure. In that process, you might get quite a bit of nitrogen leaving for volatilization. So I just wanted to bring up this quote because this is kind of the quote that I consider that really is what brought the whole term of precision feeding into the whole managing excretion and looking at the waste stream kind of point of view, that properly formulated rations that precisely meet the cow's requirements for milk production, maintenance, and gestation will also minimize excessive nitrogen, phosphorus, and potassium excretion and manure and urine. And this is really true, of course, when you're considering just the individual cow. But my question is, when you think about what happens on the entire dairy, yes, the cow is a major contributor, and precision feeding makes sense for the cow, but what really needs to be considered is what's the management dairy and how much does each cow contribute to the waste stream on the entire dairy. Because management can actually lead to quite a bit of additional waste, and if it's good management, it can actually minimize the additional waste that can end up in the waste stream. And so when you're considering managing excretion, you need to consider managing excretion, again, at both the cow level and at the whole dairy level, because it's really two different management strategies, and it's two different, almost completely different ways of looking at the waste stream. What makes some of these differences? How many different rations are fed on a dairy, cow groupings, how cows are grouped together. Are you grouping them by production level, which means that cows that have similar requirements are grouped together. And that's the advantage of multiple rations, is it gives you a chance for more precision feeding of individual groups, that you actually minimize the excess nutrients that are going into the cows, so you minimize the waste that's coming off of them. Of course, monitoring dry matter intake is incredibly important. Minimizing crude protein inputs, reformulating constantly for forage quality. All the things on this list are things that can help minimize nutrients that are going out into the waste stream, including maximizing milk production and going for maximum nitrogen efficiency down at the bottom. So that leads me right into the next section and the final section, which is actually different strategies that can be employed for managing excretion. So there's two basic topics that I want to talk to as far as strategy is concerned. I want to talk about the thought of, up to this point, we've really been talking about manure as minimizing the nutrients that end up in manure, not really considering that manure might actually have a value to it and that it could be used as fertilizer. And I'm going to explain a little bit more about that coming up. The secondary area that I want to talk then is strategies relative to feeding cows and how feeding cows can actually minimize nutrients going into the waste stream. So first off, I want to talk about what if we actually consider, instead of minimizing nutrients that end up into manure, but actually considering that those nutrients have a value in manure, and can we feed a cow so that that manure is actually more valuable as fertilizer? One of the biggest inhibitors to this is the fact that we get volatilization. And that when I'm talking about volatilization, I mean volatilization of nitrogen. So nitrogen release, because the urea in urine, when it mixes with the environment, particularly feces, which has a lot of urease enzymes in it, that actually changes the urea, and it allows the nitrogen to volatilize and leave into the atmosphere. So it does two things. It reduces the nitrogen content of manure in the waste stream. And actually, the funny thing is, a lot of our manure handling technology has actually been based on trying to actually volatilize nitrogen, and it seems like we've done things to actually increase the disappearance of nitrogen into the atmosphere. The second thing is that release of nitrogen into the atmosphere is not necessarily a good thing for the atmosphere. And so what we've done more recently is we've been trying to think about manure actually as a commodity, as something that's important, and try to find ways that we can actually capture that nitrogen and keep it in manure so that it can be a better fertilizer. This really came home when we got the first increase in fuel prices, because along with the increase in fuel prices, fertilizer prices, so commercial fertilizer prices also went up, because the two are actually kind of intertwined. And what we saw is there was a sudden interest in both farmers and dairy farmers in actually using more manure as fertilizer. But what they found is that the proportions of nutrients supplied by manure were really inadequate to use as the complete fertilizer for a particular crop. And so that's more what I'm going to talk about. Down below this list is really things that that control volatilization or have an influence on volatilization of nitrogen. So of course, temperature, air, pH. I talked about the mixing of ammonia and urea with manure, or with feces, excuse me, for increasing volatilization and releasing that nitrogen to the atmosphere. One of the interesting things is, of course, cows, because they're herbivores, they're generally naturally, their excretions are basic. In a basic kind of environment, you actually get an increase in volatilization. And if you have urea and feces mixing in more of an acid type of environment, it will actually inhibit the ureases, and you will end up trapping more of the nitrogen. So that's one thing that some people are looking at as manure additives that actually can create more of an acidic environment to actually trap the excess, the nitrogen that otherwise would have volatilized off. And of course, limiting this will be better. And a lot of volatilization, like I said before, it's dependent on facilities and handling. And in the past, we have really tried to, it seems like, almost increase the volatilization. So this is just a comparison of two of the common facilities that we have in California. Most of our dairies seem to either be freestall types, and in general, freestalls usually utilize a flush or multiple flushes within a day, and then that flush goes out to a lagoon. This system tends to volatilize around 20 to 35% of the nitrogen that ends up in the manure waste stream. And this of course, is just an estimate because, again, this is something that's very hard to measure. On average, this volatilization number probably ends up being closer to 35% or towards the upper end rather than the lower end. The second type of facilities we mainly have is what's called a dry lot dairy. So these are dairies that have cement pads with not freestalls, but cement pads with lockups that are up above them, and they're usually not sheltered from the weather. And then they'll be in a dirt pen behind that, and the dirt pen will have shade structures out in it. Some of these dry lots actually do employ flushes around the feeding area to wash the manure out of that area. But in general, dry lots, the cows spend most of their time out on a dirt lot. And what's interesting about that is when they're out on a dirt lot, they tend to pee and poop in different areas. So you don't always see the mixing of urine and feces, and it actually serves to kind of sequester and decrease the amount of nitrogen that's volatilized. Of course, a lot of this is dependent on how often those pens are groomed, how if solids might be collected, if they're doing a flush in addition to that, and if they're bringing those solids back and spreading them around the pen. So what we see here is about a range in volatilization numbers of about 2 to 37%, with actually the average being right around 12%. So surprisingly, the dry lot has a tendency to be quite a bit better than the freestall in general on being able to capture nitrogen and decrease volatilization out into the atmosphere. So when we look at what's the potential of manure to be fertilizer, one of the things that's really important to know is, of course, organic nitrogen supply in the manure versus inorganic nitrogen supply. And so why is that important? Well, the organic manure is not as available when it's applied to soil as the inorganic nitrogen is. So inorganic nitrogen would be things like urea that actually has a very high potential of being volatilized. And that, if you applied that to the plant, that would be almost immediately available for the plant to use actually as fertilizer. The problem with organic is that it tends to, when it's applied, it just sits there in the soil. And it actually has to be fermented, or it has to be metabolized by microbes within the soil, and has to be in order to break it down to get it to the point where the microbes can actually use it. And take it more into more inorganic forms where the plants can actually use it and be available. So what ends up happening is if you apply organic fertilizer, so a lot of the nitrogen that's actually in feces is in the organic form. If you apply that organic nitrogen tied up in that feces will not actually be available for the plant to use for probably about 3 to 5 years after it was actually applied. So keeping that in mind, that's really important to understand, because the relative amounts of organic versus organic nitrogen, if you're going to use it as fertilizer, if you have more organic, you may be calculating total nitrogen applied, but a lot of that nitrogen is not actually going to be available immediate to the plant. Now, if you're going to use organic sources of nitrogen and keep on applying them, in probably about 3 to 5 years, the amount of organic that you're applying will probably be equal to the amount of organic that's actually been degraded over time and is now available to the plant. So you can kind of reach an equilibrium between the two. But if you're just starting up to use this as fertilizer, this can actually really decrease your yield. And so what this is numbers from a study where people looked at, it's actually from Van Vliet et al. 2007, where they looked at crude protein percent in the diet that was fed, and they looked at, as a percentage of dry matter in the feces, they looked at amount of carbon, and they looked at the amount of inorganic nitrogen in those feces, and then organic nitrogen. And so if you look at this, you can see that as the amount of crude protein in the diet decreases, so from top to bottom, really there isn't a whole lot of change in carbon content in the feces. What you do see, though, is a very small proportion of those feces is actually inorganic nitrogen, and that's probably due to the fact that a lot of it was lost in volatilization and collection. But there's actually relatively quite a bit more of organic nitrogen in the feces, and the numbers and content for both inorganic nitrogen and organic nitrogen don't really seem to be related to the actual crude protein in the diet that was fed. Those numbers seem to be almost constant. So, and I'm going to show you some more data from this, but this leads us to believe that you might actually not be able to predict, or it makes it more difficult to actually feed based on crude protein level of the diet to actually get a specific proportion of nitrogen that's in the organic or the inorganic form in feces. And this is just a diagram that shows you what happens with organic versus inorganic nitrogen, that in different types of nitrogen that we apply. In the inorganic, it's usually, like I said, it's urea, it might be nitrates, things like that. Nitrates has a tendency to actually go with water in the soil, and so nitrates are more likely to leach through and contaminate the water supply. Urea, again, has a great chance to be volatilized even before it makes it onto being applied. And then the organic really has to go through quite a bit of degradation by bacteria and mineralization by bacteria in order to actually be available to plants. So again, this is data that was collected in California. This is showing field on 11 different dairies with different cropping patterns. It's showing you the amount of nitrogen that was input and then the amount of nitrogen that was removed through actual harvest of the crop. And my main point here is that with different dairies, different fields, the yields and the amount input don't really seem to be related. There's a lot of variability in this entire system. I actually went through and calculated what the relative yield was, so the removal relative to the amount input, and the range of numbers that you get across all of these different dairies and varieties of crops ranges from about 1.1 to 2.57. So this is all dependent on how you apply it, what the soil condition is, because you need to have good, healthy soil with a healthy, active microbial population in order to be able to use manure as fertilizer. We don't really know for this particular table what the actual nitrogen content relative to how much is organic and how much is inorganic. And if the inorganic is relatively low and this is the first time it's being applied, the plant just may not have enough nitrogen to really have high yields. And so this is another study that shows On the previous one, it was just the first application on these fields, and it showed you relative yields of nitrogen for the nitrogen input onto it as manure. This shows repeat applications actually on the same field. So we have it over two different sets, two different fields, multiple years. So we have 2001 through 2004 with a corn crop, and we have 2002 through 2004 with a cereal crop. And it actually breaks down the applied nitrogen into the nitrate, the urea forms, and then of course other organic nitrogen that was applied. And so the nitrate actually was not, that was commercial fertilizer, that wasn't actually from the manure applied. When we look at the manure applied, that was mostly the urea, which is the second, or let me see, it's actually the fourth column in, and the organic N, which is actually from manure sources. And so that total number corresponds to all three columns, but you need to look at the manure applied relative to the removal to really understand. So in other words, removal is harvest, to really understand. And so this was designed to look at and try to apply the amount of nitrogen to be about equal to the amount removed. And you can see in some cases they did really well, and in other cases they didn't do so well. So that contributes to how hard it is actually to estimate these things. In other words, the amount of urea nitrogen and the amount of organic nitrogen in feces, and from that actually look at what the total is and what the total removed is. One of the things, and then of course on the right-hand side of this table it shows you the same thing applied and removed for both phosphorus and potassium. And one of the things you can see from the applied and removed, particularly under potassium, is that potassium, when you apply it relative to manure, is potassium ended up being way over applied. So the potassium contents of this manure was too high really for what the plant needed. And again, when I talked about stratification in lagoon, this is lagoon water application. And so depending on how far down you go to actually look at the nutrient content of the lagoon, you can end up with really widely variable nitrogen, phosphorus, and potassium application, because it's very difficult to get a good assessment of how much of that is in the lagoon, because the lagoon is not uniform all the way down. The other thing to comment on is this doesn't include sludge, which if you're using lagoon water as fertilizer, eventually you have to empty out the lagoon all the way, and you have to collect the sludge that is on the bottom. And in general, at least in California, that sludge usually also is applied as manure. And sludge has a tendency, excuse me, to be very, very high in phosphorus, which will also, you can actually end up over-applying phosphorus for what the crop output ends up being. So really what this is telling you is that using manure without being able, it's very difficult to manage manure so that you actually get good fertilizer and you can actually meet the requirements of the crop to get good yields and then pull most of those nutrients off as crop yield. Another point I want to make is it's not only important when you need to empty the lagoon and to know what nitrogen, phosphorus, and potassium you would actually be using from the lagoon, but using the lagoon to fertilize, you need to pay attention to also the timing of what the application is. So this is just showing two different cropping systems. In California, we have the unique opportunity to be able to double crop and sometimes even triple crop. And so that the top graph shows you a double crop system where they're using winter forage and corn silage. So the green is the winter forage and the yellow is the corn silage. And the bottom one is a triple crop where you're using an early winter forage, then corn silage in yellow, and then Sudan silage in the fall. And so this is just showing the nutrient requirements for each crop. And this is one of the reasons why corn silage is really grown widely in California, is because it is actually a great remover of nutrients because it has a lot of requirements for nutrients. So if we look at where the nitrogen that we apply through manure actually goes. This was a study that was a little table or estimate that was done based on some numbers from the California, it was a report that was developed by the Extension Service in California to kind of talk about things about using manure actually as fertilizer and what things need to be considered. And the point of this is to just notice that when we try to use manure as fertilizer, where does a lot of that nitrogen end up going? So if we look at the top, these are just some guidelines that were used to develop the numbers at the bottom. So we assume nitrogen input to the crops is about 140 to 165% of what's actually removed. We assume that wet manure is about 75% ammonia nitrogen, and leaching, about 10 to 15% of that total applied nitrogen up on the top is actually going to be leached into the soil and then following potentially into the water. So if we use those estimates, that results in crop removal, the crop actually removing about 400 to 600 pounds of nitrogen per acre per year. The requirements of that crop were actually 560 to 990 pounds of nitrogen per acre per year. And one of the major contributors to that, if we take that 10 to 15% of applied nitrogen rule, that means that about 55 to 150 pounds per year of nitrogen is actually lost to leaching. And if you calculate the amount of irrigation water that's applied to do this, you end up with about 10 to 55% milligrams per liter of nitrogen concentration actually in that water. And just to give you an idea of how much nitrogen actually ends up being leached, is the limit for actual drinking water for humans is actually 10 milligrams per liter. So it means that, you know, this amount of nitrogen that we lose to leaching is not trivial. And again, it needs to be managed, especially if you're going to do continuous applications of manure to fields. Okay, so that was talking a little bit about strategies if you wanted to use manure and actually consider that manure has value. Things to consider when using manure actually as fertilizer, looking at organic versus inorganic sources of nitrogen from within manure. So now what I want to talk about is actually strategies focusing more on feeding cows. And these are 4 common strategies that are put out there to actually manage individual cow excretion, particularly of nitrogen. So the first one I'm going to talk about is low protein diets. The second one is trying to manage nitrogen recycling within the cow and take full advantage of nitrogen recycling within the cow. The third one is feeding diets that are balanced for amino acids. So this is usually based on the limiting amino acid theory. And the fourth one I'm going to talk about is the use of RDP and RUP in formulating diets to try to partition nitrogen in the appropriate direction for what you're trying to do. If you're trying to increase microbial yield, if you're trying to change proportions of organic and inorganic nitrogen in manure that's produced. So just kind of as a base to get started with this is data, again, from another paper. It's down in the lower right-hand corner from Nenich et al. 2005. And this is just looking, and heifers, calves, and cows looking at nitrogen and phosphorus. So on the horizontal axis, we have crude protein intake or phosphorus intake, and then we have the amount of nitrogen or phosphorus excreted. And this is just to get across the point that the more you feed of nitrogen or the more you feed of phosphorus, the more that ends up getting excreted. Just to keep in mind as a general rule as we talk about these things. So if we first talk about low protein diet, so this is probably one of the first things that was come out about being able to control nitrogen coming out in manure is to just feed a lower protein diet. And the important thing to do is to make sure that if you're going to feed a low protein diet, don't have it impacting the amount of milk produced. Because if you remember back to the beginning when I was talking about the waste stream, that one of the important ways to improve balance is to actually maximize your milk production with the minimal amount of input of protein into the cow. And so this is just another study where they measured increasing crude protein levels in the diet. So we go from 13.5 crude protein percent up to 19.4 crude protein percent. And what we're looking at is where that protein ends up in kilograms per day. So the blue bars represent milk lactose production, just to give you a gauge of what happens to milk volume produced. And then the kind of orange color is actually milk protein that ends up in milk. So what you can see for this particular trial, these particular diets, feeding more protein did not really impact milk production, or feeding less protein, if you consider it the other way, did not impact milk production. But if we look at this in a little more detail, again, with the same range of diets on the horizontal axis, you can see that if we look at how that nitrogen is actually excreted, you can see that total nitrogen excreted, of course, goes up with increasing crude protein in the diet. And along with that, urinary nitrogen also increases with increasing crude protein in the diet. But fecal nitrogen stays about the same. We do have one, at 15%, it seems like we get a little blip or we get a little decrease in fecal nitrogen. But whereas the previous slide told us that there was very little impact on milk production with decreasing crude protein in diets, you can see that actually how that nitrogen is excreted changes quite a bit with how much nitrogen is actually fed to the cow. So if we talk about low protein diets as a strategy, why would this work? Why do we think this works? Well, it's the whole idea of minimizing the nitrogen in should actually minimize the nitrogen out, and it does, as you can see from the previous slide. Along with minimizing the amount in and minimizing the amount out, since the amount of nitrogen in urine seems to be one of the most responsive areas, if you decrease the amount of protein fed, that will also decrease the amount volatilized, since that urinary nitrogen is primarily the nitrogen that gets volatilized. This is going to improve balance and increase the efficiency of nitrogen across the cow. Why might it not work as far as being able to reduce nitrogen or control nitrogen in the waste stream? Well, if you're going to consider manure and you really want to be able to manipulate manure so it actually makes a better fertilizer, you may want to actually control volatilization, try to capture more of that nitrogen, and may actually want a higher nitrogen content in the fertilizer. Because one of the things when we were talking about using manure for fertilizer is that the nitrogen content of manure tends to be way too low to get good crop yields out of it. So you either have to try to recapture more of that nitrogen in the manure if you're going to use it for fertilizer, or you need to supply an outside source of nitrogen to supply that nitrogen to those crops. So actually the phosphorus and potassium content of manure is much better for fertilizer, but if you try to apply enough manure to meet the nitrogen content, you're going to end up way over fertilizing for phosphorus and potassium. The other reasons why it might not work is if you are actually feeding more protein, you're going to increase the organic nitrogen, and of course that's going to increase volatilization. You're going to lose more nitrogen through volatilization, and you won't be able to use the manure quite as well for nitrogen fertilizer. The third one, cows' ability to recycle cows' ability to recycle urea is actually somewhat limited. The circulating pool of urea can only get to be about a certain size. So as you feed more and more nitrogen, once that urea recycling has reached its maximum pool size, and you can see it in the previous graphs, that excess urea is just going to go and be excreted. And so really what we want to find is that sweet spot where you're maximizing your recycling of urea, and that excess urea, that excess nitrogen is not going in urea that's going to be excreted. And in past, that's been set up to be about 15%, and that's been kind of the guideline for protein content of a diet. In the long run, minimizing the protein in diets may actually end up impacting maximum milk production. And where we see this is actually in large herds. Feeding a 15% crowd protein diet when you have a pen that's about 300 cows in size, you have to make sure that that diet is extremely uniform and that all cows have equal access to that diet, because the potential for variability, once again, in a really large pen means that it's highly likely that if you're not feeding a safety factor with a large pen like that, some cows will not get enough protein in their diet, and that will actually impact their milk production. So our second idea was trying to maximize ureacycline, and of course I talked about it a little bit in the previous chart, but what I wanted to do is show you two different diagrams that show low nitrogen intake versus high nitrogen intake, and this is what I was talking about with that urea pool, which is really where urea is actually recycled out of. Under low nitrogen intake, you actually see a better efficiency of urea recycling, and much less of that urea is going to spill over and be excreted into urine. But as you increase protein, you're actually going to increase, not necessarily swell the urea pool and increase recycling. What's actually going to happen is that excess nitrogen is going to come off as urea and be excreted as urine. The way that we monitor this, of course, is one of the best ways is to actually look at milk urea nitrogen. There's already been some guidelines set up for looking at milk urea nitrogen to tell what's going on with the diet, and are you meeting the nitrogen needs of the rumen, and limiting the amount of potential urea that might overflow and go out into urine. So the guidelines pretty much are that you don't want milk urea nitrogen to be above 18 milligrams per deciliter, and you really don't want milk urea nitrogen to be below 12 milligrams per deciliter. And the sweet spot seems to be somewhere around 14 to 15 milligrams per deciliter. And so usually if you're using milk urea nitrogen to assess this, that's what you're looking for, somewhere around 14 to 15 milligrams per deciliter. So the third strategy to manipulate manipulate nitrogen in manure, or actually decrease nitrogen in manure, would be to actually make sure that you are feeding so that there's no limiting amino acids. And so this graph shows you, is basically gives you an example of a limiting amino acid actually affecting utilization of another amino acid. So here, the limiting amino acid in this graph is actually sulfur amino acids. And what we're looking at is we're seeing that as we increase the amount of sulfur amino acids, which is the limiting amino acid, as we increase it, lysine degradation actually goes down. So what you're seeing is an increase in utilization of lysine because you're feeding more of the limiting amino acid sulfur, the category of the sulfur amino acids. And then you hit a point where lysine degradation, you're getting maximal utilization of lysine degradation for the amount of sulfur amino acids you've added. And so you don't really see any additional degradation of lysine, and what you actually see is that as you add more and more sulfur amino acids, lysine plateaus, so sulfur amino acids are no longer limiting, somewhere around between 0.5 to 0.55 moles of sulfur amino acids per day. And so this is just illustrating that why you want to consider amino acid balance is because when there is a limiting amino acid that's very limiting, it actually decreases it increases the degradation of other amino acids that are not being fully utilized because of this one limiting amino acid. That's going to increase degradation of amino acids. It's going to increase the amount of nitrogen that comes off, increases that nitrogen going to urine, and then again be excreted as urea, which then has the potential for volatilization. And so this is one strategy, is to actually balance diets for amino acids. So this is actually a simulation using a computer model that shows what happens in that same example with the addition of lysine, which in this particular example is the limiting amino acid, and it shows you that milk production increases drastically from 32, well, not drastically, but it increases pretty well, from 32.3 kilograms to 34.8 kilograms. It shows that there's an increase in milk protein. But what's interesting is it also shows that there's a slight increase in nitrogen in feces, nitrogen in urine, nitrogen in milk, and then the amount also of lysine in milk as it's been increased. And so this is just another example showing the impact of limiting amino acids. So in the limiting amino acids, why this concept would actually work? Well, if you meet the amino acid requirement, you're going to minimize the breakdown of other amino acids, which means that the nitrogen from those other amino acids won't be excreted in urine, and that won't be increasing the amount of nitrogen that would go into the waste stream. Why this possibly wouldn't work is because it's really hard to know what amino acids are limiting and exactly how much is limiting. There's been a lot of experiments done, and there's a lot of papers published in Journal of Dairy Science and other journals that show that what they thought was the limiting amino acid ended up not really being the limiting amino acid, and that the addition of that limiting amino acid really had no impact on production of the cow, and that particular amino acid actually ended up being excreted. Another reason, I don't have this down actually on the list, but there are some people out there that don't think that the limiting amino acid theory is actually valid anymore, and that we need to think of limiting amino acids more in groups and think of it more as a barrel and stave kind of model. And I'm not going to go much into that, but if you're interested, that might be something you may want to look at, is some of that other literature that actually thinks that there's actually a different way, there's a different reason for why amino acids are actually degraded, and that the idea of a requirement may be a little bit antiquated. So if you're going to use this limited amino acid idea, it's really important to have a good knowledge of the amino acid profiles of feed, and know what amino acids are needed for what important metabolic cow processes you have that you're trying to maximize, like milk production, or maybe microbial production. It's important, of course, to be able to really have a good way of estimating which amino acid is limiting, and to determine just how limiting it is. So, of course, requirements really in real life are not static, and requirements have a tendency to increase with the amount of production. And this is one place, again, where knowing what the variability in production of your cows are so that you can estimate what the variability in amino acid requirements are across your pen can be extremely important. And of course, one of the most important things to know is also keeping track of what other amino acids are being fed in excess, and being able to minimize those or match them to your limiting amino acid. And then, of course, some other things that are concerned down there at the bottom with, is your limiting amino acid really available to the cow and not necessarily to the rumen? And are you really going to follow the limiting amino acid theory, or is there another theory out there that may be better for estimating what the requirements of the cow are? And so this is one place. Models, of course, have been used a lot to predict limiting amino acids. And one of the things we always need to keep track of, and this is true even for the NRC models and the energy models that are out there, is that all models really, no model can represent all that there is to metabolism and physiology of a cow, but they can actually make some really good, useful predictions. And so knowing what the limitations of the model are that you're using, and understanding what conditions you can use it under and what conditions under it fails, can be really important here. So the fourth strategy for feeding was looking at proportions of rumen undegradable protein and rumen degradable protein. In general, more rumen undegradable protein means less nitrogen in urine. So rumen undegradable protein, you would expect that either the cow would metabolize it, or a portion of that is actually going to end up as not digestible in the feces. And so this plot is a plot that was done from some data that we had with looking at proportions of rumen degradable protein in diets, and where that rumen degradable protein actually ended up in feces, urine, and milk. And so this is kind of similar to that original bar graph I showed you a few slides ago. And basically what it shows you as rumen degradability increases, urinary nitrogen excretion also increases, and correspondingly fecal nitrogen actually decreases as you increase rumen degradable protein, the relative proportion of rumen degradable protein. So that just means when feces decreases, that means that the proportion of rumen undegradable protein is increasing, and so the nitrogen is passing out into the undegradable portion. But the interesting thing is milk nitrogen actually once you reach about a 10 to 15% rumen degradable protein level, milk nitrogen actually starts to decrease. And so milk nitrogen doesn't seem to be real responsive to rumen degradable protein, basically, and as long as it gets enough to satisfy the microbes to provide enough microbial protein, and then it hits a certain level where milk nitrogen actually starts to decrease. And so what I want to show you now is so I work with the model Molly quite a bit. And one of the things when I was doing a lot of this dairy modeling and looking at different ways to manipulate nitrogen so that we could actually predict where nitrogen was going to go, whether it was in urine or manure or out in milk, what I did is I did a huge literature review of probably about 19 different diets from things that have been published in the literature. And these diets, there was about 15 to 20% crude protein content on these diets. That was the range. And in these papers, they predicted, or they measured the amount of nitrogen in urine, they measured the amount of nitrogen in milk, and they measured the amount of nitrogen in feces. So this is just a plot of all of these different publications that were in the literature. And so basically what I want to show you is that there's a lot of variability in results from studies. And of course, this is probably possibly due to cows in different stages of lactation, due to different environmental conditions, different areas of the country, different feeds, all these kinds of things, different amounts of rumen degradable versus rumen undegradable protein. But I just wanted to show you an overview of where nitrogen actually ends up. And so if you look here, you can see that the nitrogen in milk is actually pretty flat. And the nitrogen content in feces, if you were actually to look at a regression line, it looks like it's also pretty flat. In fact, the only relationship that actually held between nitrogen intake and nitrogen that ended up in urine was actually, the only relationship that actually occurred was between nitrogen intake and nitrogen that ended up in urine. And that ended up being the only significant relationship. And it had actually, even though you see lots of peaks and values, the R-squared was about 70%. So it could account for about 70% of the variation. But you can see still there's quite a bit of variation across all of these different experiments. The next thing I did then, because I wanted to come up with a way to actually partition where nitrogen was going between these three areas, urine, milk, or feces, I looked at, okay, well, what if we can predict or we can know what rumen undegradable protein content and rumen degradable protein content is of that particular diet crude protein. So again, we have across the horizontal axis, I have a graph for rumen degradable protein and I have a graph for rumen undegradable protein. And both of these increase as you move across, move around to the right-hand side. And they are also both showing where the nitrogen is partitioned according to those 19 diets from the literature. We have nitrogen in urine, nitrogen in milk, and nitrogen in feces. And what was interesting here is pretty much all of these are flat. In other words, both rumen degradable protein and rumen undegradable protein didn't really seem to impact where the nitrogen was going according to the results from these papers. And again, there's a lot of variability here, and that's probably part of the reason why we couldn't really see a relationship between rumen degradable or rumen undegradable. Of course, rumen degradable and rumen undegradable protein are a percentage of crude protein, so they're both kind of interdependent. So these are not two they're not two independent sets of data. They are related to each other. In fact, the only relationship that this actually showed was there was a significant relationship between rumen degradable protein and feces, which I'm not really sure why that exists. So this was basically no help whatsoever to be able to figure out how to build some more equations into the model to get this to predict. But I thought I'd show it to you to show you that rumen undegradable and rumen degradable protein may not necessarily work for being able to predict partitioning between nitrogen in urine, feces, and milk. Why it could possibly work, and what I was thinking was, you could, if rumen undegradable and rumen degradable protein actually influence that, it would help you partition where nitrogen goes. So you could, if you were going to use it as nitrogen in manure as a fertilizer, you could pick a less volatile form. And of course, typically, rumen degradable protein is used because thinking that rumen degradable protein is mostly available to microbes. Therefore, you could possibly maximize microbial growth, and that would mean that essentially metabolize nitrogen, and that then you could track the amount of that actually ends up in urine. It doesn't look like it's actually going to work, though. Again, being able to look at that partitioning, organic nitrogen, of course, is not usually available to plants, so it would have been nice to be able to do this, but it doesn't look like from doing it from literature data is really possible. So that means that it's really experimentally difficult to repeat results looking at the partitioning of nitrogen from the basis of ruminant degradable and ruminant degradable protein. And probably we're going to have to look at other ways to actually control volatilization of nitrogen if we want to use manure as fertilizer. So that's basically what I wanted to tell you about managing excretion. In summary, I want to get across the points that nutrient balance is possible, but it's very likely that it's not really sustainable. Of course, cows are almost never in nutrient balance. They're either in negative energy balance or they're in positive energy balance. But on a whole farm basis, especially if your farm involves raising crops that get refed back to cows and you're using manure as fertilizer, you can see that what's going to end up happening is you're not going to be able to maximize yields. You're not going to be able to pull all of the nitrogen into the crop and be able to either refeed it or export that crop off. And so while you may be able to do it for 3 to 5 years, long term it just may not be a sustainable approach. Again, nutrient input guidelines can't be one size fits all. We need to consider variability, especially when feeding a pen. And that's variability, again, is one of the things not only on the individual cow level, where you're looking at individual cows within a pen, or looking at variability caused by management of the dairy. Each dairy really needs to be considered separately to figure out where their strengths are and where their weaknesses are as far as being able to track nitrogen, phosphorus, potassium, and control it within the waste stream. Flexibility in nutrient output is needed. So how are you actually going to handle those nutrients once they end up in the waste stream? Are you going to use the manure as fertilizer and supplement with a commercial fertilizer, or are you going to just consider that it's just a way to get rid of the lagoon water and you're going to spread what you have and hope it works out in the wash? That, again, along with what's important to the dairy and how the dairy is managed, all those kinds of things need to be considered when considering how to actually manage the waste stream. And then, of course, probably finally, everybody wants to find those critical control points in the waste stream that really control or can be major influences on where the nitrogen goes or where the phosphorus goes or where the potassium goes. But because of the huge variability that we have and just not being able to make those measurements, it makes it really difficult to set those critical control points. And so with that, that's pretty much the end of my talk. And thank you for listening so much. And I guess if there's any questions, it's about time for that.
So Heidi has joined us now for the live question and answer period. But before we get to that, I want to take care of a few housekeeping details. We want to talk about the next month. We will be joined by Dr. Adam Locke from the Department of Animal Science at Michigan State University. Backed by popular demand, he spoke to us in 2016, and due to his mastery of the topic, Adam will talk about supplemental facts, the myth and reality. As with this webinar, there will be 2 opportunities to join, the 9 a.m. And the 6 p.m. Both of those are Eastern Daylight Time. I want to remind you that we are also running a beef webinar series. Our next webinar will be next week with Dr. Danny Fox, and he's going to be joining us talking about growing animals. So make sure that you join that because it may be of interest to you dairy people as well. We'll be joined on September 12th by Jonas Sartori, and Nikolai DiLorenzo will join us October 10th to round out that series. We have partners in this venture, AMTS, and we are joined in the morning by Elena Bonfante from Dairy Innovations Italia. She hosts it for the Italian-speaking audience. Paula Turillo joins us in the afternoon, and Tom Long from Hemingway. We want to thank our generous sponsors who help us do this. Here in the U.S., we're especially grateful to Ajinomoto Heartland, They are superior nutrition through amino acids, makers of AgiPro-L, and Arm & Hammer Animal Health, makers of cattle feed ingredients that optimize dairy health. They are our gold sponsors. Our silver sponsors are Dairyland Laboratories, Virtus, makers of Strata with EPA, DHA omega-3s, and Prequel with omega-6s. Cumberland Valley Analytical Services, Chemin, featuring USA Lysine, Dairy One Forage Laboratory, R&D Life Sciences, and AB Vista. Our bronze sponsors are Amino Max, Purdue Agribusiness, Jeffo, Quality Liquid Feeds, Adiseo, Origination Inc., and Novita, makers of Nova Meal. I'm going to open up the floor for questions. I have some in my comment box and in my chat window, if I can. And so I will go ahead and handle those as we come and see if Elena has any questions from the European perspective. I need to make sense of things. First, we're going to do a little bit of mic checking. Heidi, can you speak?
Yeah, can you hear me?
Yes, I can hear you. I hope other people can too. And Elena, can you speak?
Yes, can you hear me?
Yes.
Okay.
Could you hear Heidi?
Yes, I could.
All right, good. It seems like we're all working now. I guess I will lead with a couple questions that I have had, if I can manage to see that chat window. Here we go. I have sympathy for our people when we change our program platform and they're wondering where everything went. This gives me greater sympathy because it's tough when you have to learn something new. Who moved my cheese? So the first question I have is from Steve in Idaho, and he asks, is there still a stigma that phosphorus needs to be added to diet for better reproduction? How is this affecting mass balance? Can you speak to that, Heidi? And Elena, I'm going to mute you while she gives her answer.
Okay, so at least in our area, most of the concern with reproduction is actually on energy and not necessarily phosphorus. That's what we've been seeing in a lot of our experiments and a lot of our on-farm work. So if you're actually feeding phosphorus to increase reproduction or increase pregnancy, yes, it would increase phosphorus that ends up in the waste stream.
Okay. Let's see. The next question I have is going to be, this is a comment. So in New York State, there's a lot of drag hose incorporation of manure, and it's limiting the loss from volatilization, the nitrogen loss from volatilization. Is that being advocated in California and across other parts of the U.S., do you know?
What was the dry something or other that you said?
It's drag hose incorporation of the manure. So.
Oh, okay.
Yeah.
So it's in the way that they apply it.
Yes.
Yeah. Of course, application, the methods of application are really important. But unfortunately, most of the volatilization actually occurs before you actually apply it. And so incorporating the liquid directly into the soil, of course, is really important to trap what you have. But most of the volatilization I'm talking about actually occurs before that.
Okay. I'm going to give Elena, do you have any questions or comments from your experience there in Italy?
Yes. Now, I'm talking about the volatilization of nitrogen. Do you have any suggestion about an acidificator or acidifier to use for manure treatment?
No, and it hasn't been widely used actually in California because in acidifying, you're actually going to have to add probably a mineral or, an acidifier generally is a mineral that's a charged particle potentially that would be added. And so if you're going to do acidification to trap the nitrogen, you've got to consider that if the addition of those minerals will actually increase the salt content in the manure that you're actually going to apply to the land. And so this has been a trade-off that hasn't really been explored a whole lot, and that has stopped people from going the acidification route.
So it's a strategy that you don't use at all there?
as far as I know, no one is really using that. I think it's being used somewhat in the lagoons, but it would require a lot of acid to be applied to a lagoon to get that to work.
Okay. I have another question. I mean, first of all, a comment probably related to the strategy that evaluate the rumen digestible protein and ruminant digestible protein. I think that you have to look also related to the rumen digestible proteins. You have to look also to the carbohydrate fermentability. What do you think?
Oh yes, definitely.
Okay.
If the diet's not balanced with both available carbohydrate, and rumen degradable protein to maximize microbial production, either direction can result in more nitrogen actually being excreted. And that, if you look in the guidelines that I gave you for milk, urea, and nitrogen, it actually included guidelines also on what's going on with the carbohydrate relative to what numbers you have for milk, urea, and nitrogen.
Okay.
Thank you, Elena. Do you have any more questions?
One more.
Okay, do you want to go ahead since everything's working so well?
Now, since we are in summertime, right, and we are soaking cows all over Italy pretty much, most of all in these days, this is going to impact, of course, the amount of manure that the farm produce. So, in this case, do you have a priority in order, either the cow cooling, to prioritize cow cooling or the manure amount?
I think definitely you've got to prioritize cow cooling.
Okay.
In California right now, we are in our summer also, and particularly in this area of the state, it's extremely hot. We haven't had excessive heat like above 110 degrees, and I'm sorry, I don't know what the conversion is to Celsius for that, but we've been over 100 degrees up to around 105 degrees for over 30 consecutive days. So, and it doesn't cool down a whole lot at night. We get maybe a 20-degree drop at night, which is not real great for the cows. And so if you don't cool the cows, cow comfort is a big issue. You're going to lose milk, and again, maximizing milk production is a great way to get rid of nitrogen. And so in that model actually that we did of an existing whole dairy, cow cooling was one of the contributors to the waste stream. And I don't think you can dairy if you can't keep the cows comfortable.
No, of course. No, and probably there is you can, of course, timing, the soaking period, or use a strategy in order to soak the cows in a certain time of the day, that more during the day than during the night, for example. Do you?
Yes. Yes, all those things are very important.
Okay. Thank you.
Thank you, Elena. I'll ask a few questions here. So, work done again in New York State with mass balance found that the price changes in fertilizer and feed drove mass farm level nutrient balance response on the farm. Do you see the same with your farms? Was any economic work done in conjunction with your farm level nutrient balance work?
Not that I know of. Most of the economic part of it, it's been mostly, at least from my perspective, it's been mostly seeing what happens with the cost of commercial fertilizers versus using manure. And so and of course, all of our farms have to file nutrient management plans. And so those are kinds of the main drivers of being able to drive farm balance.
Okay, thank you. So with regards to the slide that you had, or the discussion that dry lot was better than a freestall, have you quantified management tactics to amount to the amount of loss? For example, how much does daily lot grooming or feed bunk flushing contribute to the change in nitrogen loss from volatilization for leaching? And did you measure leaching?
No.
Okay.
We haven't done that much detail. At least I'm not aware of it. We've mostly just looked at emissions of nitrogen in the two relative systems.
Okay. And I think I have one final question, unless Elena has something. With regards, I have two actually. Have you done any studies or comparison of limiting emissions and excretions of grazing versus conventional feeding dairies?
No. In California, we do have some grazing dairies, and but as far as I know, that would, on the emission side, you'd probably be more in the Frank Mitloner area. And as far as I know, I don't believe he's done a comparison of grazing systems versus concentrated feeding dairies.
Yeah. It would be interesting because you have all of the dynamics that go into that with regards to efficiencies and production. So
yeah,
that's
yeah. You know, in California, one of the limitations is our land is extremely valuable. So when we talk about, you know, at least down here in the Central Valley, when we talk about putting animals out on pasture, they're actually out on marginal rangeland, and so it's a little difficult to do some of these measurements in areas where it's pretty steep and rocky, and yeah.
It's clearly not being used for crop production.
No, right, exactly.
I have a question from Umberto Francesca. His question is about the impact of the trend in dairying of the mega farm that would pose on the environment, and if the government is going to impose new regulations on them, if you're aware of any. So that's sort of a big question, I think.
It is huge, and you know, of course, in the United States, the political climate really drives what's going on, and our political climate has changed, and we don't really know what's going to happen. California sets its own regulations. The federal government sets regulations for the entire United States. California sets regulations that are usually much more restrictive than what the United States does. And so that, in part, whether that's going to merge together or whether California is going to get more restrictive, at this point I don't think anybody really knows.
Right. I think we have to wait an election cycle or two to find that out.
Yeah, there's some rumors going around that some restrictions from the federal government is going to say that states cannot set restrictions on their own, which means California would now have to go back to the federal government restrictions, which would actually be much looser than what we have right now.
That's interesting.
Yeah, and that's I don't know if that's going to actually happen or not, but that's one of the things that's out there.
Yeah. Question. I attended a cheese conference last week, actually, at which the people from Fiscalini spoke, and they talked about their use of digester and how they use that to handle the whey produced in the cheese production and also just the manure from the farm. And I was recalling your chart that said that a lot of the nutrients are in the liquid portion and that's cycled back through for flushing, et cetera. In some of your discussion of mass balance and application of the manure to the fields, would that change considerably if there were more digesters used? And is there an increase in digesters since you did that study?
Yes, probably on both. Right now there are two grant programs for dairies in California. One of them is kind of limited, but it's encouraging dairies to actually put in digesters. And the other one is for encouraging dairies to use other manure handling technologies to decrease nutrients in their waste stream, or increase recapture of nutrients within their waste stream. And so we had a period of time where we knew that digesters were great for using nutrients in manure, but the problem was we had a diesel rule coming down, and the air boards were saying that the equipment that's used to generate power from digesters would not meet the air requirement, for clean air in California. And so we had two committees or groups of committees in California that were actually handing down regulations or ideas that were completely conflicting. Now that has been mitigated, and so they are back to encouraging digesters.
Okay, interesting. I wonder, is that a California-based encouragement? Because it seems like a lot of alternative energy usage programs went away with the change in administrations for us.
Yes, both of those are California-based.
Okay. Unless Elena has some more questions, I think that we have exhausted the questions here in our morning webinar. Heidi, you'll join us again this afternoon. Elena, I'm going to unmute you and see. Hi, Elena. Did you have any more questions or considerations?
No, I'm okay. Thank you.
Thank you, and we appreciate you joining and also giving an opportunity to speak about it from the European perspective, because I know that you guys are doing maybe more with measuring these emissions. Is that correct in saying?
It depends on the area, but yes, we are having more and more restrictions actually. So it's going to be a big deal in the future.
Yeah, I think all the some of the stuff that Heidi talked about, in that it's variable and it's all reliant upon management, that seems like that's going to be something that we'll really need to tighten up, because the regulations will eventually happen if they haven't already.
Yeah.
Paula, do you have questions to start off?
Yes, I have one. The first question is from Carlos. Which are the strategies to buy feed to minimize nutrient excess?
Really big question.
Yes.
And I can pretty much just speak to experience in California. What we do here is our forages are primarily grown on farm, affiliated with the dairy. So that's our manure actually gets used as fertilizer on the forage ground, because you can't apply manure to human edible crops. And so what our dairies end up buying then is corn, in other words, concentrates, soybean meal, canola meal, all of those other supplements that get imported by rail car from other areas. But primarily the forages are what's actually raised on farm. And that's because of the limitations. That may change here, but that's because of limitations of cost of land, water availability, and our farmland is very valuable because we can grow things like almonds and fruits and other things like that that actually have a higher value than cow feed. So we feed a lot of byproducts.
Okay.
Paula, do you want to keep going, or shall I ask some?
I have one more.
Okay, go ahead.
This is from Danielle. Compost barns are effective systems to retain more nitrogen?
Is that a question?
Yes.
Okay.
Sorry.
Yes, composting, if you're doing it correctly, it involves taking down and introducing oxygen, because you're looking for an oxygen-based fermentation to heat up the pile and kill any microbes really in the pile. So composting, if you're doing it in the true composting form, if you're not just piling up solids or manure and just letting it sit there, if you're actually incorporating oxygen into it, you actually increase volatilization with composting. And in fact, there's been limitations, at least in California, on being able to compost because it does increase volatilization. And so our air boards have been trying to discourage composting. In the true sense of composting.
I think Paula's question was also directed towards composting barns, where the cows are actually housed on compost-bedded packs.
Oh, so you mean, in other words, using manure as bedding? Manure solids?
Yes, but I think, there's been a little bit of talk more about compost-based barns. It's a little different than using... Paula, can you address that better?
Yes, with compost barns, I mean like a dry lot, but with a roof, and then they work the soil to compost the bed, the manure and everything excreted on the soil.
Yes, that's the diagram that I showed that compared freestall flush dairy to a dry lot dairy. That's correct. The dry lots, or what you're calling a compost, what I believe you're calling a compost barn, actually is on average much better at sequestering nitrogen and keeping the nitrogen from being volatilized into the environment. That's correct. Does that answer the question?
Yes, okay. I think so. Compost bedded pack barn is another term for it.
Okay.
Yeah. I have a question from Tom Long, and he says, to continuously use the model, how frequently should we measure outputs of the farm, and where are critical points of measurement?
So that's the problem with the model, is that the standard deviations on the original estimates that we built the model on were extremely large. And so that kind of precludes using the model as to actually pick where those critical control points are with being able to control volatilization and also manage excretion. So I don't think the model really can be used to select out those critical control points. And what was the other part of the question? I'm sorry.
Let's see. How frequently should we measure the outputs of the farm?
Oh, okay. So that was part of the point of the model also, is that you have to be very careful when measuring the outputs of the farm, because even if you want to know what the nitrogen, phosphorus, and potassium content of the lagoon water is that you're going to use for application, the first part of the lagoon that you pump out to go and apply it, that composition is going to be different from the last part of the lagoon that you pump out to apply, because the lagoon has stratification within it, that there's different microbial metabolism going on throughout the lagoon, and the composition at the top part of the lagoon is going to be very different from the composition at the bottom lagoon, and including the sludge at the very bottom of the lagoon. So things like doing mixing the water in the lagoon before it gets applied, or even measuring, which is now possible with some of these NIR machines that they have that can do real-time nitrogen estimations at least, but actually measuring the manure or the lagoon water as it's applied can actually maybe be one of the best places to find out exactly what you're applying to the land.
Okay, thanks. So I have another question from Tom Long, and he's asking, is the manure model actively built into ration models like CNCPS? Heidi, I know you've worked a little bit with the CNCPS, and maybe you can address that. I know we have a whole excretion side to the program, or incorporated into the predictions.
So the manure model I printed that I showed you guys is actually not been even published. So, and it's based on numbers that we got from measurements on a real dairy. So I haven't actually contributed to, in the Molly model that I work with, I'm not really trusting how it's partitioning out the nitrogen myself. I'm not as familiar with how the Cornell model actually separates nitrogen into urine, feces, and milk, and so I can't really comment on, validating that or even explain how that part of it works. So, sorry.
I actually think I can get some information to Tom about that, because I know that Caroline worked a lot in that side of it when it was being developed. All right. I have a question on a couple questions in watching the video. On the slide that's on the forage input and in relation to yield removals, that was dated 2001, with some of the updates in the following slides up to like 2003 Has there been analysis of what sort of changes have we experienced in crop yields that would change those numbers? Because it would seem to me over the past 15 years or so, there's been some considerable breeding that would have increased the yields per acre, whereas the manure production is fairly static in terms of what would be put on. What do you have to say to address that?
Yeah, and so obviously yields have increased quite a bit. There's a tremendous amount of precision crop technologies that have come into play in the last 15 years, including things like being able to minimize the amount of water that you apply on crops through irrigation, using different irrigation techniques, aerating the soil, all sorts of things, being able to actually do real-time measurements of nitrogen in a crop as it's harvested. I mean, just huge amounts of being able to really get down to almost, because of GPS, mapping fields and getting down to almost nitrogen yields on a 1 square meter area of a field. So, I mean, the technology, since that data has been examined on multiple different dairies, has really increased. Probably what has not changed is our technology as far as are we just trying to get rid of the lagoon water and use it as another irrigation and kind of make up the difference with other commercial fertilizers, or are we actually trying to manipulate the manure output so that we can actually minimize the amount of fertilizer that we pull in from other sources? And that's the part that hasn't really changed.
Okay. Paula has some questions, so I'll let her go ahead with some of them.
Yes. Another question from Carlos. Could we reduce the nitrogen excreted in feces by using tannins?
Oh, by using tannins.
Yes.
It would reduce it somewhat. I don't know if it would be a significant enough reduction. I do know that tannins, yes, it does reduce it, but I'm not exactly sure of how much reduction you can get in using tannins without, so I don't know if you're talking about feeding higher tannin feeds or just adding tannins to the amount that's excreted. If you're feeding it, you're going to run into limitations on being able to actually start limiting the nutrients that the cow can actually absorb and use. So I can't really give you a number, but yes, it should decrease it.
Great. Another question from Leonardo. Could the use of limiting amino acids be an effective method to improve feed efficiency, knowing that we are also increasing excreted nutrients?
Okay, I'm a little confused by the question because it seems that if you are increasing the excretion of nutrients, you're actually decreasing feed efficiency. Can you clarify a little bit more?
I will try, but he's trying to know if the use of limiting amino acids could be an effective method to improve feed efficiency.
Yeah, and I'm not sure how that would be used.
Okay.
I'm not sure, and I think I just maybe don't understand the question.
Maybe. I will try to clarify it.
Okay, thank you.
Okay, I have another one from Julio. What happens to the nitrogen after using manure in a biodigester?
That's a really good question. And we still end up with, of course, in a biodigester, the gas is actually trapped within the covered lagoon. And what you're actually mostly extracting is being able to burn off, produce energy from the gas that's produced off of that digester. And most of what's being burned is actually not nitrogen. So I imagine because it's covered and because you're not really burning nitrogen, that actually is that's actually still within the manure. And if anything, it's going to concentrate it because you are going to be burning off carbon substances.
Great. And the last one. When you using liquid manure spread on the soil, did you analyze the impact on other minerals such as sodium and sulfate, and the possible leaching?
Some of farm advisors have done that, and I believe those particular data on those is actually in that report that I mentioned, but no, I did not. Of course, I didn't include it in that kind of detail in this presentation. But if you would like more information on that, I believe it is in that report.
Okay, thanks. I will ask Marian the report if we can have it.
Sure.
Yeah.
Okay.
A question from Tom Long. Any way to redesign the lagoons to minimize variability due to stratification while hopefully not consuming more energy?
Not that I can think of. That's one of those million-dollar questions. If I could figure it out, I'd probably quit my job and go into business for myself. But doing things like lagoon additives, increasing purple sulfur bacteria, which can help with sequestering sulfur, things like using the appropriate amount of mixing. So you don't want to mix too much to incorporate in a lot of oxygen, because the idea of a lagoon is actually to increase anaerobic fermentation, kind of like a big rumen. And in part, that's what introduces the stratification. So maybe if the lagoon was mixed right before, right before the water was pulled off to go to irrigation, that doing something like that probably would help. And a lot of that lagoon water is actually used in flushing, and so through the flushing process, some of that is, there's some mixing that's going to occur on a daily, within a day. It's probably going to be like 5 or 6 times, depending on how often the dairy actually flushes.
Okay, thank you. I'm going to ask a couple of the questions from this morning and one that I did not. This was in regards to the leaching in dry lots. Did they check also for the local wells for nitrogen contamination?
At the time that data was collected, we weren't really doing test wells. Since then, test wells have become much more common. Regulatory agencies are actually pushing those. And one of the issues that we have in this area is just because you have nitrates or high salts in your test well doesn't necessarily mean it's from manure application, because this particular area of California actually what used to be a large swamp. And so because of that, through irrigation, building of the aqueduct, and farming, waterways were built to control the water and keep California, this area of California, from being this big freshwater shallow lake. But because for so many years when we get rain and the flood would come into that area, and I'm talking like probably 1940s, the salt concentration in our soils is already pretty high. And so that's why I'm saying that the dairies do contribute, but we already had a problem even before we were doing, probably had a really bad problem before we were doing much farming or doing much dairy farming.
Okay, and for the benefit of the listeners tonight, this is a question that I asked earlier, is in New York State, we're using drag hose incorporation of manure, and that to limit loss of nitrogen. Is that being advocated in California?
Yeah, they're advocating, well, it's direct incorporation below the soil surface to minimize volatilization. I don't know about drag hose specifically, but most places are, not everyone, of course, some people still spread it by just, spraying it on top of the soil, but most people are actually trying to incorporate it into the soil, because that, again, reduces volatilization, like and gives you a better efficiency. It reduces volatiles going off into the air. So, that's always one of the better ways of doing that.
And I think part of the reason here that they're using a lot of the drag hose is to decrease the compaction of the soil for us because it's less weight going across the fields.
Yeah. Out here, almost everyone is using no-till or low-till agriculture, where corn is actually basically planted in the stubble.
Yeah,
so,
I saw a lot more of that this year, actually, than I noted in previous years. So this is a clarification of the question that Paula was asking earlier. In the slide that you showed 2 diets, one adding lysine. In the diet that added lysine, it is more efficient, but the nitrogen excretion is greater. Could you explain more about that? Do you want me to load the slide set so that you can?
Yeah, that would be great. That would.
I think so. Let me check with Paula. Does that look right to you, Paula?
Yes, I think this is the one.
Okay, thank you.
Yes.
Okay, so this slide shows where lysine was a limiting amino acid. They added more lysine, and in theory, what this should do, if you can identify what the limiting amino acid is, in theory, that should increase your production and decrease your excretion, so that you actually excrete less nitrogen or excrete more nitrogen in feces relative to the amount of nitrogen that you're excreting in urine. Because in the limiting amino acid theory, if you have an imbalance in amino acids, you are actually going to use more amino acids for, you're going to deaminate them, and you're going to actually, that excess nitrogen then will go off as urea and be excreted, which should increase the amount of nitrogen in urea and decrease the proportion of nitrogen excreted as feces. Does that make sense? I hope. So if you're talking about increasing efficiency of the animal, if you're trying to feed a more imbalanced diet, you'll actually be decreasing the efficiency of the animal, which would be like milk output relative, or milk nitrogen output relative to milk nitrogen input. But if you're talking about efficiency as far as being able to put more nitrogen into manure relative to the nitrogen that goes out in urine, I still think that probably feeding a better balanced amino acid diet will still get you a better profile of nitrogen that's excreted and possibly volatilized versus nitrogen that would be in organic forms that would stay in the soil for 3 to 5 years and then become available.
Great. The Leo says it's okay.
Okay, so
you answered the question.
Oh, okay, good. Okay, good.
Paula, do you have any more questions?
No, I don't.
Okay. I also do not have more questions. So unless I get... is are heavy metals a problem in the manure as well? This is from Tom Long.
Any mineral is basically a problem, and particularly in our herds, and I think across the United States, nutritionists have a tendency to really overfeed zinc, copper, and manganese, because there have been shown some benefits to doing that. And when I mean overfeed, I mean overfeed relative to NRC requirements. And so, yes, that's going to increase their excretion, and you're going to end up with more of that in the manure that could be applied to the soil and cause more problems.
Well, everybody should tune into the November webinar, because Bill Weiss is going to talk about mineral recommendations. So maybe we can hone in on those in that webinar. If no one else has any questions, I will thank you, Heidi, again. This is the second time we've talked today, and I think other than me fumbling around for files, it seemed to go pretty well. Paula says thank you, and they really enjoyed the webinar down in Argentina. So,
oh, great.
Yeah, thank you everybody that joined. And by the way, you got much easier to hear after the initial panicky 5 seconds. Panicky on my end. It's always tough when the person answering the questions can't be heard.
Yeah.
Tom Long says thank you very much. So I want to thank everybody for joining us. Make sure to check out the webinar with Danny Fox next week, and come back and come to the Nutritionist. Oh gosh, September 12th, I believe, is the date with Adam Locke. And I will get this processed and recorded as soon as possible, but as always, there seems to be a bit of a lag time. I think there's other things that I have to do this next month, so it's going to be a challenge. Heidi, thank you. And thank you, Paula and Tom, and also Paula Allen, who is our translator. She always does a great job. So thanks very much. Goodbye, everybody.